Assalamualaikum and good day everyone. Let's continue our quantum chemistry lecture with properties of wave function. I have mentioned to you that the requirement for wave function or property for wave function, first it must be square integrable. Okay. This requirement is because you want the probability density to be finite. Okay. So if you try to integrate, you will get one. That's why the wave function must be square integrable. Second property is that it must be single valued. Meaning that if you have wave function, okay, it must be single valued like this. Okay, it cannot be like this because why? When you try to find the probability, you will have many multiple values. Okay, and then finally the wave function must be continuous. And the first derivative, okay, must also be continuous. Meaning that you cannot have wave function things like this, okay, like tangent, okay, where you have a discontinuity at this point, okay. This one is not acceptable. This one is acceptable. This one is not acceptable, okay. So those are the three properties or requirement of wave function that I have told you, okay. There are other additional properties that I have not told you, okay. The first one is that the wave function is not must be, but the wave function are orthogonal to each other, okay. We will look at what does it mean by orthogonal, and then the fifth one, the wave function can be written as a linear combination, okay? Linear combination. So for example, if you are talking about a particle in a box, okay, you have the wave function psi n, okay, equals to square root 2 on L sine n pi L multiplied by x, okay. But you can combine all this wave function to write it as, so you can combine it, meaning that you have to add psi n equal to 1, psi n equal to 2, psi n equal to 3, and so forth, okay. So you can written it like this, and then psi n x, okay. This is what it means by linear combination. So this thing you will have sine sum. This is sigma is just stand for sum, okay. Square root 2 on L sine. Okay, now let's move on to orthogonal, okay. I'm going to explain about it a little bit. Okay, in 2 dimension, okay, if you have x and y, when they are perpendicular to each other at right angle 90 degrees, okay, you call it perpendicular. Perpendicular. That is for 2 dimension, okay? But in quantum mechanics, you can have many dimension. In fact, the dimension is actually infinite, okay? So in that case, we use the word orthogonal. Meaning that the wave function are at right angle to each other. Now, if the wave function is orthogonal and normalized, we call it orthonormal, okay? This means orthogonal, okay? They are at right angle to each other, and normal for normalized, okay? Okay, right. Let's look at the property of orthonormal wave function, okay? We have something in mathematics that we call Kronecker delta function, okay? Meaning that if you take inner product, okay, of 2 wave function, for example, if you take wave function m, x, okay, you take inner product or you multiply by psi n, okay, and then it is equals to 0 when m not equal to n. And then this inner product equals to 1 when m equals to n, okay? So this is very important because if you still remember, okay, if m equal to n, okay, you will have x m and then multiply by m equal to n, okay? So your n is actually m, okay? This is just the same as the probability density. Okay. That is why if you try to integrate this thing, okay, if you take Bond's rule, okay, minus infinity to infinity, you will get 1, okay? So that's why this orthonormal property is very important for any wave function, okay? Okay, so if we now look at this wave function for particle in a box, okay, let's take for example wave function when principal quantum number n equal to 1, okay. If you take 1, it is 2 on L, okay, n equal to 1, it becomes sine pi L multiplied by x, okay. Okay. Now let's look at for psi n equal to 2, okay? So psi 2 is equal square root 2 on L sine 2 pi over L multiplied by x. So if you are trying to find kind of like, if you have this particle in a box, okay, this is where n equal to 1, and then you have n equal to 2, okay. The wave function looks like this, and then it looks like this. So if you try to find the inner product for n equal to 1, okay, so it just become psi 1 square root, psi 1 square. It gives you the probability of finding a particle, probability of finding a particle in n equal to 1 state, okay. That is when you take the inner product for psi equal to 1. But what happens if you take the inner product, okay, psi 1 multiplied by psi 2, you get 0, okay, because of those that I told you, okay, psi m, psi n equal to 0 when m is not equal to n. Why? Because it, if you think it logically, it does not make sense to find a particle uh, in n equal to 1 and n equal to 2 simultaneously, okay? It will just give you 0. But if you take psi 1 multiplied by psi 1, you get the probability of finding a particle in n equal to 1 quantum state, okay? Or quantum number. Okay. This is very, very important, okay? This Kronecker, we call it Kronecker delta function, okay? So if you have a wave function 1, okay, sorry, m, n, it is equal to delta function m equal to 1, okay? This is, you immediately know that delta function is defined such that it is 0 when m not equal to n, 1 when m equals to n, okay? That's it, okay? Because later on, we will see that when you want to find the probability density, you will need to use this rule, okay? This rule is very, very important when you want to find the probability density. You have looked at this example for the last question in tutorial 2, okay? When I give you the wave function for psi 0 plus psi 1 plus psi 2 plus psi 4, I think, if I remember it correctly, and then you need to find the probability density, so you need to square everything, okay? Once you square everything, you will see that psi 0 multiplied by psi 1 or just give you 0, whatever psi 0 multiplied by psi 0 will give you 1, okay? Wherever you see the indexes, okay, this is what we call index or subscript, okay? When you see the index are different, this term just vanish, it becomes 0, okay? Okay, right. Now let's move on to linear combination, okay? Linear combination is very, very important because actually in quantum mechanics is that it's kind of an order or instruction that you must write the wave function in terms of linear combination, okay? Another word, we call it superposition. We will see another example of this linear combination when we will learn about hydrogen atom or helium atom later in chapter 9 or 10, okay? So this is a must. So if you are given any wave function, okay, for example, any wave function psi nx, you are given something like normalization constant multiplied by Gaussian function nx, okay, you must take the linear combination, okay? So the wave function is actually the sum n goes to infinity for psi n, which is equal to sum n goes to infinity an normalization constant and some function, okay, just g. I just call it g, okay? You must take linear combination, okay? It will be clearer if we look at this example in hydrogen atom when we learn about hydrogen atom, okay? That's it. Thank you very much.